Hello everyone, I'm Dhanush Verma. So I'm going to talk about the final project presentation. In the next slide, we can see the table of contents. And coming to the introduction, the final project basically focuses on the development and enhancement of a CNN model specifically tailored for image classification, utilizing the CIFAR-10 dataset as the benchmark. The CIFAR-10 dataset presents a formidable challenge due to its diverse range of images presenting 10 distinct object classes. Unlike simpler datasets like NIST, which consist of handwritten digits, CIFAR-10 encompasses complex visual scenes with variations in color, shape, and background. The overarching goal of this project is to refine the CNN architecture and training process to improve its accuracy and robustness in clarifying CIFAR-10 images. By leveraging TensorFlow, a versatile deep learning framework, and adhering to the project guidelines to avoid using Keras APIs, the endeavor emphasizes a rigorous approach to model development and implementation. Through a systematic methodology encompassing data preprocessing, model construction, training, testing, and process evaluation. This project aims to demonstrate the iterative nature of CNN development. By iteratively refining the model architecture, optimizing hyperparameters, and incorp- incorporating advanced techniques such as dropout regularization, weight initialization, the project endeavors the push to push the boundaries of CNN performances on the challenging CIFAR-10 dataset. Ultimately, the insights gained from this project contribute to the broader discourse on deep learning methodologies for image classification tasks. So coming to the next part, so this is about a data set which was instructed by the professor in the instructions. So the data set which I have chosen is annotated image dataset of household objects, where the creator of the dataset is RoboFEI at home. This team created the annotated image dataset of household objects mainly to aid in the development of object detection systems for home robots. It is composed of two sets of annotations on images, each with a distinct function. So contents in the dataset one, in this whole datasets, there are two subsets. So coming to the first subset, there are 166 images which are annotated, and there are 1028 objects and 13 classes are available. And in the second set, there are 388 images which are annotated in total. There are 1737 objects and 20 classes. Coming to the data structure, the pictures are in JPG format and the comments are made using labeling, and the videos are in MP4 format. I mean, the videos are like the test videos and test pictures without labels. So the dataset serves the purpose of offering the fundamental resources needed to develop unique object detection systems. Users can use the provided videos to analyze inference time or use the annotated images to train and validate their own models using test images. And the availability of the dataset is Like the information provided does not include any links to download, but the dataset is, the accessibility is in the internet. So coming to the next part, so this is the data preparation for the actual project, final project, where we have downloaded all the 7 dataset files, data files listed in CIFAR 10 dataset from our Canvas modules, and then accessed a remote virtual machine using SSH in the Google Cloud, and opened the Jupyter Notebook subfolder in a remote virtual machine. Created a new subfolder named CIFAR 10 dataset under the Jupyter Notebook, and uploaded all 7 files into the remote virtual machine from my PC by selecting the upload files option. So coming to the next part, which is CNN setup and overview. Here, the CIFAR 10 datasets convolutional neural network. The architecture consists of 2 main phases, which is decision making and image processing. It begins by ingesting colorful images measuring 32 into 32 pixels. It then goes through 2 rounds of clarification and evaluation. In the first round, the CNN uses 32 different filters to recognize basic forms and patterns in the images. It then compresses the image to highlight the key elements. It uses 64 filters in the next round to go deeper and find more complex patterns before further reducing the size of the picture. CNN makes conclusions regarding the visual content after analyzing the images. This can be done by running the compressed image through a number of layers until a categorization is formed. Following the completion of the image analysis stage, CNN moves on to predict the image's content. This can be done by running the reduced image through a layer made up of 1024 neurons, then determining how confident it is in these predictions. During training, the CNN forgets certain information at random to avoid overconfidence while supporting more balanced decision making. During the training process, the CNN learns to enhance its predictions by adjusting its parameters using an optimizer known as ADAM. The CNN's capacity to recognize images will continuously advance over time due to this iterative adjustment. The trained CNN is then tested on an independent dataset in order to determine how accurate its predictions are. This CNN architecture has shown encouraging results, proving that it can identify pictures effectively and with accuracy. Therefore, it is a useful tool for applications like object recognition in images. And the results are the CNN achieved an accuracy of approximately 67.35% on the CIFAR 10 test dataset after 5,000 training steps. The accuracy steadily increasing during training, indicating that the model was learning effectively. The highest accuracy achieved was 68.99 at step 4600, while the lowest was 39.24 at the step 100. So coming to the next part, the CNN model performance evaluation. The CNNs were used in this part to categorize pictures from CIFAR 10 dataset. The dataset was divided into training and test sets with 60,000 and 32 into 32 color images spread over 10 classes. Two convolutional layers, max pooling layers, a fully connected layer, and a dropout layer made up the CNN architecture. The output layer used the softmax activation function, while the convolutional layers used ReLU activation functions. Using the Adam optimizer and a batch size of 100 images, the model was trained for 5,000 steps at a learning rate of 0.001. To avoid overfitting, the dropout probability was fixed to 0.5. The test dataset was used to assess test accuracy at each of the 100 steps. On the CIFAR 10 test dataset, the CNN obtained an accuracy of approximately 67.35% after 5,000 training steps, with the maximum accuracy reaching to 68.99 at step 4,600. Overall, the CNN model performed moderately when it came to identifying CIFAR 10 images. Even if the accuracy increased gradually throughout training, the model's performance could have been improved with additional optimization and hyperparameter and structural adjusting. However, this effort provided some insight into the process of developing the refining CNN models for image classification tasks, showing the importance of trial and error to achieve the best outcomes. Coming to the comparison with other datasets and improvements. So I have also used the NIST dataset for homework assignment 4, which consists of handwritten digits that are quite easy for computers to recognize. With this dataset, I was able to achieve an accuracy of 99%. Whereas in the final project, I have used the CIFAR dataset, CIFAR 10 dataset, which offers some more complex tasks, similar to the colorful photo album filled with various images of cars, animals, and other objects. Computers will find it more difficult to understand the images because the variations of forms, colors, and backgrounds. Using CIFAR 10 dataset, I was able to achieve 67.35% of accuracy. When compared to NIST dataset, the CNN CIFAR 10 dataset has lower accuracy. The below chart shows the training and validation accuracy of a CNN and NIST and CIFAR 10 datasets. The x-axis represents the number of epochs and the y-axis represents accuracy. The CNN achieves higher training and validation accuracy on the NIST dataset compared to the CIFAR 10 dataset. This is likely because the NIST dataset is simpler, containing only handwritten digits, while the CIFAR 10 dataset is more complex, containing images of 10 different object classes. The possible reasons for the lower accuracy in the CIFAR 10 dataset are as follows. CNNs are like skilled de detectives when it comes to teaching computers to recognize images. They find patterns in images to determine what's within. The curves and straight lines of digits are examples of relatively simple nest patterns, animal shapes, and the textures of vehicle and boats are examples of complex CIFAR 10 patterns. Two solutions can be applied to improve CNN's ability to understand CIFAR 10 images. Firstly, the network's learning process can be improved by giving it more training examples. A bigger and more complex dataset helps the CNN identifying objects more accurately, much as people do as they are exposed to more images. Furthermore, improving the CNN's design can improve its functionality. Improving the design and complexity of the network makes it more capable of spotting even smaller patterns in the images. Therefore, by adding additional images to the CIFAR 10 dataset, the improving the design of the CNN, we can greatly increase the computer's ability to correctly classify these complex images. And in the next part, we can discuss the improvement convolutional neural network performances. And here, there we can observe few improvements such as increased in depth of convolutional layers. In this section, I have increased the depth of the convolutional and also increased the depth of the filters, which allows the network to learn more complex features, and also added dropout regularization in the fully linked layer. Dropout regularization has been applied with a zero point 0.5 dropout probability by randomly removing units during training. This helps to prevent overfitting and ensures the network applies effectively to new input. Increase the training steps, which is another improvement, where the number of training steps have been increased from 5,000 to 6,000, allowing the model to train a longer duration, which can give better convergence and improved accuracy. So, improved initialization of weights and biases. This is one of the improvement in the performance. Here, the biases are initialized to a constant value of zero point 0.1 and weights of convolutional layers are initialized with a reduced normal distribution with a standard deviation of zero point 0.1, and better resolution during training may be enhanced by this initiation method. And the next one is adjusted learning rate. Here, the learning rate for the Adam optimizer has been set from 0.001 to 0.002, which might help in achieving faster convergence and better accuracy. The next one is increased number of filters in convolutional layers. The number of filters in the convolutional layers have been increased, allowing the network to capture more diverse features from the input images. The whole the whole conclusion for this improvement is all these changes compared to the part 4 homework, including increased depth of convolutional layers, dropout regularization, and improved initializations of weights and biased like contributed to achieving better accuracy on the CIFAR 10 dataset. And comparing the accuracies, the modified CNN on CIFAR-10 dataset achieves a higher accuracy of 67.35%, whereas in part 4, I have achieved 67.29, indicating that the modifications made have been effective in improving the performance of the CNN model. And here, coming to the next part, we can see the observations. Here in the first observation, we can see CIFAR 10's complexity necessitates deeper CNN architecture and sophisticated training approaches for optimal performances. And also the techniques such as data augmentation and transfer learning prove instrumental in enhancing CNN performance on challenging datasets like CIFAR 10 datasets. And in the next one, while the CNN model displayed commendable classification capabilities on CIFAR 10, there remains scope for further refinement and optimization. In the next observation, we can see the understanding dataset intricacies and selecting appropriate training methodologies are pivotal for achieving optimal CNN performance in image classification tasks. And coming to the conclusion in the next part, so here I also want to mention one thing, that in the rapidly evolving field of artificial intelligence, convolutional neural network have emerged as a powerful tool for image classification tasks. These networks are particularly adept at analyzing visual data, making them indispensable in various domains such as computer vision, robotics, and healthcare. However, achieving optimal performances with CNNs requires careful design, training, and fine tuning to address complexities inherent in real world data sets. And coming to the conclusion, here the completed project demonstrates how CNN models are developed and improved upon iteratively for image classification tasks through the utilization of TensorFlow, annotation dataset analysis, model architecture optimization, and enhancement implementation. The project contributes to the progress of CNN comprehension and utilization in intricate image recognition scenarios. To attain even greater accuracy rates, future work might entail more structural modifications and hyper hyperparameter testing. All things considered, and the complete project which demonstrates how CNN models are developed and improved upon iteratively for image classification tasks. Through the utilization of TensorFlow, annotation dataset analysis, model architecture optimization, and Enhancement implementation. The project contributes to the progress of CNN comprehension and utilization in the intricate image recognition scenarios. To attain even greater accuracy rates, further work might entail more structural modifications and hyperparameter testing. All things can be considered, and the project advances the continuing development of CNN techniques for various real world uses. And here in between, I have forgot to mention uh, about one thing in the comparison of convolutional neural network performances, where the possible reasons for the lower accuracy in the CIFAR 10 dataset are because of the skilled detectives when it comes to teaching computers to recognize images. They find patterns in images to determine what's within. The curves and the straight lines of digits are examples of relatively simple NIST patterns, and animal shapes and textures of vehicles and boats are examples of complex Sifar 10 patterns. So this one I have missed previously. Sorry. And this is the project presentation. Thank you.